welcome to one day's course. So today it's my pleasure to introduce one of visitors from Santa Barbara, Professor Fouque, and he will talk about linear-quadratic stochastic differential games on directed chain networks. Let's welcome.
Thank you very much. Thank you so much for having me. So this is my third visit to Taiwan, and I always enjoy and I like the hospitality of my former PhD student, Sean, from NC State, and Leo from Santa Barbara. So it's always a pleasure to visit you. Have a good time here. So I see that many students or postdocs, and so I will try to go slowly. There are plenty of details here, but I want to explain what we are trying to do and what are the methods and what we get out of it. So it's more mathematics. There is no, I don't want to talk about directly application, but more on the mathematical motivation. So this is a joint work with PhD student Yichen Feng. She finished, she defended in December. Now she's working at JP Morgan in New York. And Tomoyuki Ichiba is a colleague. He's a professor at UCSB, and so we have been working as an expert in stochastic portfolio theory, if you know what that is, you know, intersection of one motion, local time. So he's more a probabilist, and he knows quite a lot. Okay, so what I want to discuss here is first directed chain. So what we mean by directed chain is that everybody think about this. For us, it can be a particle, but later on it will be an agent. We'll be talking about games, so it's more like an agent than an individual. So in the directed chain, this arrow means that agent 2 is affecting agent 1. So there is a link, a directed link. So this one will be affecting this one, number 3 will be affecting number 2, number n will be affecting number n minus 1. And so this will be a finite directed chain. Of course, we need some boundary condition, I will specify that. Or it can be infinite. And in fact, we will pass to the limit of an infinite directed chain. Or it can be periodic, like here. And here you have a periodic boundary condition. Here I have to give you some boundary condition. Here this is simply periodic boundary condition. And then n goes to infinity, we'll see what is happening. So now the motivation is why we want to do that. Well, this is in contrast to, so we're talking about networks. Think about networks of agents, and there are links between agents. And these are the two opposite, these are the two extreme kind of networks. This network is where everybody is connected to everybody, but fully connected network. And at the opposite, this is, oh, you are connected to only one. That's exactly the opposite. Oh, you could be connected to nobody, but again, that's not very interesting, right? So we try to understand what will be the behavior of system, and I will describe the system, between this, where everybody is connected to everybody, or affected by everybody, and this one where you are only affected by one, but that one is affected by the other one, affected by the other one, so indirectly you are affected by everybody. Affected, not infected. Yeah, you could look at epidemic, but I'm not talking about epidemic. I don't wear my mask. So what we will be doing, this will be more related to mean field gain. We will talk about mean field gain because you are affected by the empirical distribution of the full system. And that's what we will see in a minute. But here it's completely opposite. There is no mean field gain at all. You are affected by only one. Okay, so let's look at now a little bit of mathematics. So let me go slowly. So each agent is represented by a diffusion. That is state. The state of agent I is given by a diffusion which depends on t, evolution of t, and there is a parameter u. So let me describe that. So this is the differential equation that agent I is following. So first you have a noise. So each agent has its own noise. All those noises are independent, and you see that what we call the volatility is 1. That's constant here in this case, or of course we will do better than that. But let's assume that. But what is important here is drift. So the drift term depends on the position of the agent, the level, if you say the capitalization, these are banks, because these are capitalization, so the drift will depend on the capitalization of the institution, but it depends on everybody else through that term. So let's look at this term. There is a parameter u, which is between 0 and 1, and which tells you if you are more in the fully connected case or the directed chain. So if u equals 1, these completely disappear, and this is what you have, and now you see this is a distribution of the next one. So this is a directed chain. Right? Your drift is affected by the distribution, the empirical distribution of the next agent. But if u is 0, then this is fully the empirical distribution of the full system. So u equals 0 is more like the fully connected network. U equals 1 is a directed chain, and in between. We have in between, right? For any value of u in between. Okay, so any question at this time? Is that clear? So you have a system of SDEs, and those SDEs are coupled through the distribution of the others. Right? It's a typical situation. Okay, so this system, there is no gain. Everything is prescribed. So the dynamic is prescribed. And this is something we have studied with another colleague of mine, Detering, at UCSB, with also Tomoyuki Ichiba, published in this journal, SPTA. And we studied the behavior of this system. No gain, no control, nothing, just so let me try to summarize what we observed. So, and what is interesting is n goes to infinity, because then you get nice formulas and everything simplifies a little bit. So we are interested that n goes to infinity. So here's a limit. Here's a limit of one agent. This is one agent when n goes to infinity. So this agent has its own one-hand motion, but the drift depends on the position of the agent. This is a given agent. I'm looking at one of them. And it is affected by the distribution of what? So this is what I want to describe now. So if u equals 1, it is affected by the distribution of another agent, fictitious agent, which will represent the full chain, so that the law is the same. It has the same distribution, the same law, but this agent is independent of this one motion. So this is a little bit new. So maybe let's start with u equals 0. U equals 0, so we have only this term, and now you are affected by the law, its own law. The agent is affected by its own law, and you know how this SDE are called when u equals 0. So you have only the law of xu right there. You know how this is called? No? What kind of SDE that is? Makin-Vlasov SDE. Nobody knows that? No, you know. Yeah. Makin-Vlasov SDE, it means that you are affected by your own law. So this is the situation. If I go back here, that would be that situation. So with n finite, you are affected by the empirical distribution of the full system. When n goes to infinity, this empirical distribution, by the law of large numbers, will converge to the empirical distribution of one of them. And that's exactly what we describe here. I have a little bit of trouble here. So this is exactly what we describe by this law of x. So you have to think about this SDE as a limiting distribution of one agent when n goes to infinity. If it's fully connected, you have only the law of the agent. That's called Makin-Vlasov. It's a mean field limit. It's called mean field limit. You are affected by the mean field. Now, as the opposite, if u equals 1, then this is a directed chain. There is no mean field anymore, and this is what's going on. You are affected by by the distribution of someone, another agent, not independent, but this agent is independent of that Brownian motion. So basically, if you remember the picture, I'm not going back because it takes time, but you are affected by the next one, you are an agent, you are affected by the next one, this will be the next one. It has the same distribution. When n goes to infinity, everybody will have the same distribution. That's kind of easy to understand. But then, because this BT was here, number 2 was not affected by number 1. Number 2 was affecting number 1, but number 1, it didn't affect number 2. So that's why this x tilde, which is number 2 if you want, is not affected by the Brownian motion of number 1. So this is kind of a new form of an SDE. It's the opposite of Makin-Vlasov. Right? And that's a little bit weird to picture. Right? But you have to keep in mind the picture of the directed chain. You are affected by the next one, which has the same distribution. And you understand when the chain is infinite, it doesn't matter where you are. The distribution will be the same, but you are not affected. The next one is not affected by the previous one. And that's exactly what is going on. So, and of course, when I pick u between 0 and 1, I have a mixture of these two. This distribution is a mixture of these two. Okay. And I want to understand the behavior of this SDE. So it's an infinite dimensional SDE because it depends, right here it depends on distribution, so it's infinite dimensional in some sense. And this is infinite dimensional because it depends on the next and on the next and the next, right? It's like the chain, the system is infinite dimensional, and the SDE looks like one dimensional, but it's infinite dimensional in nature. Right? So we want to understand that, and in order to do that, we will look at the sample case. So to make things a little bit simpler, we can compute. We look at the case of the first infinite dimensional, but we'll take the linear case. Right? We take a linear drift. So this is the drift that also. So if you look at it, it looks like an OU, right? An Orstein-Uhlenbeck process. Everybody knows OU process, Orstein-Uhlenbeck. It means that you are attracted to your mean. Right? So for instance, here you see I am attracted to my mean. That's an OU, Makin-Vlasov OU. But in this case, you are not attracted to your mean. You are attracted to the next guy, right? Which has the same distribution and all this. And a combination of the two, right? And it is on. So we start. Let's say we start from 0, right? To simplify everything. And if you start from 0, the first observation is that when you take the expectation here, you easily get the 0. Right? When you take expectation, you have the expectation. This is 0 because the expectation. This is 0, right? So the solution is simply 0. So we know what is the expectation in this case. That simplifies a little bit the analysis. Okay, so actually, so this is, we can solve explicitly. Everything is Gaussian. Right? It may be infinite dimensional, but it's Gaussian. So because the equation is linear, everything is Gaussian. So the only thing you have to do is to compute the mean, and to the mean we have it already. We did the computation of the mean, and to compute the variance. And actually, you can solve exactly. We can give a form of the solution. The solution is given by this. So if you look at that, this is simply the solution of an OU process. But you have this guy in between, and this guy can be written in function of an infinite number of Brownian motion. So that's why it's an explicit formula, because I can write this in terms of an infinite number of Brownian motion, and it enters in the first one. Right? So there is a little bit of work to do that, but it's not too complicated because things are Gaussian. It's a Gaussian computation. So that takes a little bit of time, but it can be done. And this kernel here can be computed explicitly. Okay, so those Brownian motion are independent and independent of the Brownian motion. So this describes exactly the solution of this equation. Okay, so let's go a little bit further. So without computing the variance explicitly, so you can understand that from those formulas you can compute the variance. If you are good at computation, you go and you just compute the variance. So here is what is happening. And I summarize. So we look at the interaction type. The interaction type depends on U. U equals 0 was a pure mean field, fully connected. U equals 1 was pure directed chain, and U in between, it's a mixed interaction. So that's what we described previously. We can look at the asymptotic variance. It means that you look at one agent, and you look at the variance of x of that agent as t goes to infinity. Asymptotic variance, what happens when for the variance? Actually, you see that in all these cases, this variance stabilized. It means that there is a limit. The variance has a limit, it's stabilized. But in this case, when it's purely directed chain, it doesn't. The variance explodes. So it's very different. The behavior between mean field and directed chain is very different because of this. Even in the variance, you see it. Now, of course, this is when you look at one agent. You could look at two agents and look at the correlation. So for instance, in this case, in the mean field, the agent become independent. So this is in the mean field limit, and this is called propagation of chaos. But in physics, this is propagation of chaos. That's where Makin-Vlasov started. As for two particles, if you have many of them, and they depend through their mean field, they become independent. So at the beginning, they are independent, in between they interact, but in the end, they become independent. And that is only in the case of pure mean field. As soon as you put a little bit of a directed chain effect, they are dependent. They don't become independent. Okay, so this is a description of what is happening in this very simple infinite dimensional system of SDE. It's not so simple, but you can compute explicitly, and this is a description. So, I have to point correctly. So now we want to introduce a game feature. So do that if I can point, that would be easier, if you don't mind. So we want to introduce a game feature. So here we didn't have a game. The agent, suppose we are trying to describe an institution, banking. The banks usually, they make decisions, right? They try to cut the cost, increase the profit. They do this decision. And so the question that we wanted to look at is to put a game structure in a model and try to see if the dynamics that we described previously is the equilibrium of that game. Is it the Nash equilibrium of that game? Intuitively, this is what I had in mind actually. I wanted to prove that this simple dynamics that we had before was the Nash equilibrium. This follows, Leo, you should remember, this follows what we did in your PhD thesis, right? So, in a different model, but that was the idea, right? You have a sample model that you can describe. Let's see if that is a Nash equilibrium of something more complicated. The answer was yes. Here the answer is no. Oh, that's so. Yeah. And the answer is actually interesting, as you will see. So putting a game, we will start with n player, and we will do only directed chain. We will not mix the two things. We will do it later, but just the directed chain. Because the mean field, we know well the mean field. This is called mean field game. Who has heard about mean field game before? Mean field game is a theory developed in 2006 by Pierre Williams and Lasry from the PDE point of view, and another team in Canada, Kern, Malamé. And so this has been very, very interesting. So there is a PDE approach, there is a probabilistic approach, in particular the work of Carmona and Villarue. So there is a lot of things going on with mean field game. So here we are not looking at mean field game. We will go back to mean field game later on, but we are looking at the case of directed chain. And we saw that this has nothing to do with mean field game. Right, so this is a work that we did with Ichiba and Tomoyuki, published in this journal. So first we consider the pure directed chain. Right? U is 1 to make things simpler. So let me describe the game. The game I'm considering, and keep in mind that we wrote this game, and in my mind the Nash equilibrium for this game should be the one we described before, and the answer will be no. So what is a game? First, we want something linear-quadratic, so we can compute. In general, linear-quadratic you can compute. You can compute the Nash equilibrium. So it's linear in the sense that institution I or agent I has a control of its drift. Alpha I is a control. So the institution I will choose that control. Of course, there are some conditions on the control. It should be adapted. You cannot see the future. There should be some square integrability condition that I didn't write. There are some assumptions on the control. To be admissible, the control should satisfy some assumption. But here is a control. That's the evolution of the state of agent I. And I have n of them. We start at time 0 from a given random variable, and they're all the same IID distributed at the beginning. And we assume that they are centered at the beginning for simplifying a little bit our life. But now we have to say what the agent is trying to do. So the agent is trying to minimize this value. Well, minimizing in finance, we always minimize. In general gain, you maximize. You always don't want to maximize. In finance, you minimize because most of the time it's a cost. You don't maximize the reward, you minimize the cost. That's why. That's perfectly equivalent. So we want to minimize this. And what is that? So this is, there are two parts. There is a running cost. So this is a running cost. You integrate from 0 to capital T. Capital T is a maturity, right? Fixed maturity. You integrate that, and there is a final value, terminal cost. So it's called running cost, terminal cost. So in the running cost, you have alpha I squared. This is a price to pay to control. No matter what, if you want to the alpha going up or alpha going down, negative, you pay the square. It's kind of transaction cost, if you want. Square. Right? No matter the direction, you have to put energy in the system. And now this is the interaction. So if you look at this interaction, this means that this is agent I, right? This is for agent I. Agent I wants to be close to I plus 1. Because he wants to minimize the square. Epsilon is positive. It's not small, it's just a positive number. So this means that agent I wants to be close to I plus 1. That was our interpretation of I plus 1 is affecting I, because I wants to be close to I plus 1. Right? You see? Okay. So this is the directed chain, if you want. That's where the directed chain is. If I had the empirical mean of everybody, that would be mean free gain. I'm not looking at mean free gain. So directed. And same thing in the terminal cost. It means that I wants to be close to the next one at capital T, and there is a square. So it's a linear quadratic problem. Now, of course, epsilon is positive, C can be positive, or 0, it doesn't matter. You can remove C if you want. But what you need is some boundary condition, right, for the last one, because the last one, there is no n plus 1. So either you have a free boundary condition saying that the last one is autonomous. When you pick I equals n, then you remove that part here. That is autonomous. It doesn't control it, it's just a diffusion. Right? The last one is a diffusion. That's a one of the free boundary. Or it can be periodic boundary condition, and then you don't need anything else. Simply n plus 1 is x1. When I equals n plus 1, this is n plus 1, and you remember the circle, right? Okay. So several types of boundary condition, and we will let n goes to infinity anyway. Okay. So I just described that we are looking at a linear quadratic differential game on directed network. Interact with exactly, that's exactly what I described. Right? So we want to solve that and see what is happening. And solving means what? Solving means trying to find the Nash equilibrium for this game. So everybody knows what is a Nash equilibrium? Who doesn't? Don't be shy. You don't know? Who does? Be careful, we'll ask you. Who doesn't? Who doesn't? Now be honest. Who doesn't know what is a Nash equilibrium? So you all know. I can go fast. Nash equilibrium is very easy to understand. Everybody is happy. It's a state. It's a state where everybody is happy.
You watch a movie, so you know.
Oh, you watch a movie?
Yeah.
Beautiful mind. But I don't talk too much about mathematics in a movie. So John Nash, I had the privilege to meet him once at Princeton. John Nash is a brilliant mind. So everybody's happy. It means that you have a state where if one agent tries to do a little bit differently, he will not gain anything. Everybody's doing what they have to do. One agent is trying to change a little bit to do better. He can't. He won't do better. So everybody's happy, and that's Nash equilibrium. Okay? So this is what we are looking at. We are looking for Nash equilibrium. The way to treat that. So the first thing, there is here a subtlety between open loop and closed loop for those control. And this is hidden in the admissibility of alpha. It depends how you define what kind of control the individual can use. Open loop means that you can use only the information of the Brownian motion. You don't observe the position, just observe the noise, the Brownian motion. Closed loop, you observe your position. So your decision can be a function of your position. It can be Markovian, for instance, if you are a function of your position now. That's a Markovian control. But here we simplify, we'll just look at open loop. Open loop is a little bit simpler. It's simply, you make your decision simply looking at the Brownian motion, not your position, not the x. You look at the b, but not the x. Right? Or the w's, but not the x. That's open loop. Okay? In the end, when n goes to infinity, they will be the same. In this case, so that's why I'm not bothering too much, but there is a difference between the two. So the way you do that, you introduce an Hamiltonian. This is from physics, right? You introduce an Hamiltonian. The Hamiltonian has the state variable, so these are the state variable. The control, of course, you get the control, and adjoint variable. So you introduce adjoint variable. So n adjoint variable for each individual. So you have Yij. So Yij is a matrix. And so the Hamiltonian is given by what? So you have the value function, the objective function, the running cost. So this is a square. This is your running cost. So you recognize the running cost. The terminal cost is not in the Hamiltonian. And then of course you have this term here which says that this basically is the adjoint variable is the derivative of the value function. When you write a PDE for diffusion, you get the drift times the derivative of u. So this plays the role of the derivative of the value function. This is called the adjoint variable in the Hamiltonian setting. Once you write this Hamiltonian, so this is a definition of the Hamiltonian. Once you write the Hamiltonian, and of course this adjoint process, I have to tell you what they are. And once you write this Hamiltonian, what you will do is use what is called the stochastic maximum principle, Pontryagin maximum principle. So I don't know if you know that. Now we are in the area of control and gain. So the idea is to minimize the Hamiltonian, and find the trajectory for the forward equation, x is forward, and the backward y, that I will explain in a minute, so that there is a solution which minimizes the Hamiltonian. And Pontryagin tells you then you have computed the equilibrium, one equilibrium. Right? So what is the equation for the adjoint process? It's a backward stochastic differential equation. So now you see we are getting in the area of forward-backward stochastic differential equation. So it's a backward. So how do you obtain this equation? The differential of your adjoint process is given by the derivative of the Hamiltonian with respect to the state. You take the Hamiltonian, you take the derivative with respect to the state. You put a negative sign because you go in the backward in time. That's why you have a negative sign. And then plus the noise. You have all the collection of the noise, and you have to put some thing in front of the noise which are part of the unknown. So these are part of the unknown. They should be, if you want a solution, they should be adapted. They should be adapted to have a solution. So when you solve this equation, and you have a terminal condition, the terminal condition is given by your terminal value, the differential of your terminal cost, right? So this is a differential. Your terminal cost was square of that. So you have the two disappear with the 1/2, which was here, And then, of course, you have to be careful because you differentiate it's I and j, so you have to take care of all the indices, right? So you have this difference of delta function here. So this is a terminal condition. So for example, if c equals 0, you don't bother much. The terminal condition is 0, right? C is 0 terminal, but it's a backward equation, right? It's a backward equation. So you have, and solving this backward equation is finding y and z. Finding y and z adapted. It's backward, but they need to be adapted. Right? And then what is the choice of alpha? Alpha has to minimize the Hamiltonian, so I didn't say. You can see, maybe I will write it in a minute. Minimizing the Hamiltonian with respect to alpha is easy. You differentiate with respect to alpha I. You take the Hamiltonian and you differentiate with respect to alpha I. So it gives you an alpha I here, and here it gives you alpha, yii equals 0. The derivative should be 0 if you want the minimum of the Hamiltonian. So your alpha at I should be minus yii. Right? So this is how it goes. So in this equation, we will replace this alpha by the minimum of the Hamiltonian. Okay, so now, so if I compare, I have two forms for the y here. I can write my. So let's see if I. What did I do here? Did I went too fast? No, I didn't go too fast. Yeah, so this is what I was telling you a minute. This is how you find your optimal alpha by differentiating the Hamiltonian. So this is your optimal alpha. And now you put that in your forward-backward equation. And so the forward-backward equation was the one previously that I showed previously. You inject that in your forward-backward equation. And your linear-quadratic, and of course you have to take care of the boundary condition. Let's say, in this case, periodic case. And then how you solve, in general, how you solve linear-quadratic forward-backward equation is by guessing the solution. You know that the value function should be a square. So the y is a differential, is a different derivative of the value function, so it should be linear. And this is your guess. So you want a y which is linear in x. It's a linear combination of all the x's. And of course, what is unknown are the coefficients. Those coefficients depend on t also. But they are deterministic. You want this to be deterministic. So your ansatz, your guess, is that the y is a linear combination of all the x's, but you don't know yet the coefficients. If you can find the coefficient, then you have solved the problem. Right? So those are deterministic scalar function. Of course, you know the terminal condition. Terminal condition should be given to c. If c equals 0, then this is 0. And you know. Okay. So non-stationary free body. So it depends on the boundary condition that we will put. Let's say. So the forward equation. That's your forward equation. So now the alpha at is here with our ansatz. So this is a forward equation. And now you have the ansatz. If you look at this forward equation, it means that x will be interacting with all the particles in front of you. Right? So it's a little bit different from what we had in mind, interacting with only the next one. No, it will be, it will be interacting with all of them. Right? But we still have to compute those numbers. So this is our ansatz. We differentiate the ansatz by Ito's formula. You will get and you compute here correctly because you have many indices. You have to be careful. You apply your Ito's formula. Io knows that very well, right? Not on that one, but very equivalent. Mm-hmm. So you apply your Ito's formula correctly, making sure that you get all the terms. And then you compare with the other. You have already an equation for dy. Negative, the derivative of the Hamiltonian with respect to x. You have already an Ito's formula for dy. You have another one. You compare them. You want the martingale term to be the same. You want the drift to be the same. Because we know that an Ito decomposition is unique. Right? We have to apply all we know in stochastic calculus. You're okay with stochastic calculus, right? When I say that, it's fine. Right? Yes? Ito's formula, everybody? Ito's decomposition, martingale part, drift. Yes? Okay, good. So I do that. I compare the martingale term. If I compare the martingale term, this gives me the z's. The z should be given like this. Oh, but then, okay, so you say, well, z is given with respect to the phi, but I don't know the phi. Yeah, but it's not too bad, because phi will be deterministic. So this means that z, if I know the phi, I know the z's, and they are deterministic, so they are adapted. Right? So check. No problem with the martingale part. But I still have to find the phi. And now I go to the drift, and I compare the drift, and that gives me, oops, yeah, fast. So this gives me the drift. So this is the first phi with 0. It has a differential equation. The second one, it has a differential equation, and up to the n-1 plus a boundary condition. So this is my boundary condition, or free boundary condition, depending on the boundary condition you put here. Right? So this is a system of ODEs now. That's a system of ODEs, nothing random anymore. And I want to see that there is a solution to this system. Right? For my FBSD to have a solution, for my answers to be correct, I need to show that this has a solution. And what is that solution? I'm interested in exactly what is the solution of this system of ODE. So that should be simple. You say, okay, system of ODE, I go back to some years ago, and it's a little bit messy. The difficulty are the red terms. This is the interaction between all these equations, and this is the difficulty. So let me show you. So of course you can write this. It's a Riccati equation if you think about it, because these are square, right? These are products. These are quadratic. So this is called a Riccati equation, but it's a matrix Riccati equation. And matrix Riccati equation has been studied a long time ago. There are books on it. And sometimes they have solutions, sometimes they don't. And here our goal, our task, is to show that we are in a case where there are solutions. Because if there is no solution, we have not solved the problem. Right? Okay, so this is the way to write in a condensed way what is the matrix Riccati equation. Okay, so let's say if you do the periodic boundary condition and we let n goes to infinity and we do some numerics. First, we do some numerics, and we look at what these phi functions are doing. Actually, you see the phi functions are doing that. The first one goes to 1, the second one goes to -1/2, and all the others are going to 0. So this is what the numeric says. I let n goes to infinity. Here n is 100, n equals 4. So this converges to 1, this converges to -1/2, and all these they converge to 0. What you see here close to t is a boundary effect at capital T, which is not very important. So intuitively, and I'm not intuitively, but numerically, it seems that the first one goes to 1, the second one to -infinity, and all the others to 0. But we have to work on that. And what is happening with, if you remember those red terms, the quadratic terms, was the unknowing terms, and those unknowing terms, numerically, here's what they do, they go to 0. They disappear. So for the periodic boundary condition, this is still open to prove that. I don't know how to prove it. Numerically, it works well. But on the free boundary condition, that's I know to prove. So this is intriguing because I cannot prove that. I worked hard on that. We worked hard. We couldn't prove that. But this goes to 0, it seems. But so if we use the other boundary condition, so we can describe the infinite player game. So the infinite player game is described like this. This is described by this infinite sequence of numbers, which are solution of these SDEs. So you see the first SDE is here. That's a pure Riccati equation. It doesn't depend on anybody else. The second one depends on the first one. It's a Riccati because it's quadratic, and it depends on the first one. And the case one will depend on all the k-1 before. Right? So this is a type of Riccati equation which seems nice, and n goes to infinity, so it's an infinite system. So the way to attack this is to use a moment generating function. So you introduce a moment generating function of this system of phi's. As you see, the moment generating function is a function of z, and of course you have to avoid confusion here between the index and the product. And this is the equation that the moment generating function satisfies. So the moment generating function satisfies something simple. It's a Riccati equation. if it's a Riccati equation, I should be able to solve it because now it's one-dimensional, right? And this is when you take z equals 0, this is what gives you this. Yeah, actually, the phi 0 is the sum of all the others. There are nice relation in these things. And to go a little bit more precisely, so under equilibrium, so this is our equilibrium. Now we have a solution. Under equilibrium, it's like an infinite dimensional Australian-Beck process where the xi is attracted to everybody else, but with some weight. Right? You are attracted to the next one with huge weight, 1/2, and then it decreases. The weights are decreasing. So now, this is the way to write it to see that it's an OU process, attracted to everything. So you see that this is where we see that the equilibrium is not the first model that we studied. Because the first model we studied, it was only attracted to the next one. And here you see that under equilibrium, in fact, everybody counts. Yeah, everybody in the chain counts. Right? So that's where it's different from the model that I presented. And that was a little bit of a surprise. So now I want to be even more explicit than that. And to be explicit, I pick epsilon equals 1, give you the epsilon, and I take capital T goes to infinity. So I look at the stationary solution of this Riccati equation. That's easier. I could do the full thing, but so if you do that, if you take T to infinity, you have now numbers. They are not equation anymore, they are numbers. So phi 0 is 1, phi 1 is minus 1/2, and you have this relation, all this relation between all your numbers. It turns out that this relation is related to Catalan numbers. Anyone heard about Catalan numbers? Yes, you did? He was doing number theory. So you should know Catalan number, right? This is where they appear. And it's in a funny way we find those Catalan numbers here in a game theory, which is a Catalan number. They have probabilistic interpretation. But this is interesting. This is related to the Catalan numbers. And from there you can compute them. Actually, here's a computation of your numbers. They are given by that. These are the computation of the Catalan numbers. Right? So they are explicit. And the beautiful thing is that you can associate the Markov chain to it. So instead of considering the phi, you introduce a minus phi, which are probabilities. So P1 is a probability half, and then, so this is half, and then Pk can be computed, and these are probably the sum is, you can check that the sum is 1. And so these are probabilities. And then, of course, you can associate a transition matrix. So that's transition matrix for Markov chain, right? P1 plus P2 equals 1, the sum is 1, so that's a generator, right? And you can associate what we call, then we introduce that, the Catalan Markov chain. Catalan Markov chain is exactly given by this. Here it's an infinite dimensional one in motion, and this is a Q matrix, so X is infinite dimensional, and that Q matrix is the one that we involving the Catalan numbers, and this is your equation. So it looks like an OU, and this is what we have. Why I'm telling you that? Because then you can compute. Then remember, for instance, what we want to compute is a variance of one. One agent, I want to compute the variance. Right? So, and actually this matrix is very nice. If you go back to the matrix before, you can show that Q square is a Jordan block matrix. That Q square is very simple. And because Q square is very simple, you can compute all the powers, and you can compute the exponential. Right? So this is, you want to compute this exponential of a matrix, so you have to compute all the powers, and because of this nice property, you can do it. It can be done, and here is the answer. Boom. You have to work with it. But here is the answer, and you see that you have a function. You have this row function. These are your boundary. So these are stochastic integral, but not really, because this is deterministic, right? We call that the small integral. How do you call that? The small integral? The Wiener integral. It's a Wiener integral. It's not a Nito's integral. And so, but you have this function here, and when you do the computation, these functions are associated to Bessel function. So this is like computation. It's not very complicated. You have to pay attention and do it correctly. You get your Bessel function. Here is a kernel involved in the Bessel function. I mean, these are classical functions in mathematics. But what is nice is that with all this formula, all this work, now I can tell you what is a variance. The variance of one individual in equilibrium, in a Nash equilibrium of this game, here's a variance. Big. And now, remember, we were saying as t goes to infinity, what this variance is doing? I can take t and let it go to infinity, and I have it. This is the limit, 1 over square root of 2. This is interesting because in the first model, the variance was going to infinity. Here the variance stabilized. This is the main difference. If you look at the equilibrium, it's very different from the model that we looked at first. It's a Catalan evolution, and this Catalan evolution stabilized, and you can compute the variance. So all this work for that, basically. So, and the dependence persists. You still, I didn't put the covariance because the formulas are big, but that is in the paper, and the covariance stays. So the dependence persists. Okay, so now, of course, I could go to, we'll try to make it short. I could go to the mix of the two. I could restore the mean field game, remember? And now what will be? So still the same thing, you control, and now in your objective function, what you do, this is a part of the directed chain, like before, with a u, and with 1 minus u, you have the mean field game where this is a mean. So if you deal with a finite number of agent, you put the empirical mean right there. If you start with infinite dimensional, you have to be careful because you cannot do the empirical distribution of an infinite system, right? So yeah, you have to put directly the mean right here. Same thing for the terminal condition, and then n goes to infinity. So this can be computed. So that's what I was saying. You have to be careful with the interpretation of this. For finite agent, this is that. But for infinite agent, it has to be the mean. Okay. And so again, so this is a game, and we want to see the behavior. I will go fast. You do exactly the same thing. You write your FSD, the Hamiltonian, and you compute. What is happening is that you get the same Catalan Markov chain, except that it's skilled. The midfield game aspect gives you a Markov chain which is killed process. You know what that is. After an exponential time, you kill the process. Right? So this is exactly what is happening, and you can compute the variance. You can compute the variance, and this is a variance which is here as t goes to infinity. And so everything is computed. And here's a table. So asymptotic variance stabilized, the dependency persists. So this was, what is black is everything like before. It didn't change from before, but the main thing is this. If you have pure directed chain, then the variance is stabilizing, not in the other case. So all this analysis to compare this. Now so that's one thing. One thing to, now for instance, if you think about application, let me comment quickly on application and we'll skip the rest of the mathematics. If you think that a system of agents are in interaction, let's say social networks, whatever is the situation, and you would like to decide if it's a mean field interaction, like everybody is affected by everybody, or you are affected by the next one who's affected by the... Are you in a directed chain, or are you in a mean field? Or is this agent? How do you decide of that? This is a good criteria. This is a good criteria. Look at the asymptotic variance. If the asymptotic variance explodes, that's mean field game. You are affected by a lot of people. If you are affected only by one in a directed chain, then the variance will stabilize and you can conclude. So, and there is a filtering. You can do filtering without, so this is in the paper, so I'm not getting into it. So this is one application is by looking at the state of an agent, you can detect if it's connected to a lot of people or not. Now, another thing that I didn't do is I presented the mean field game, so the mean field setup, and the directed chain, and this is the two extreme. What is in between? In between, it's a huge amount of things which can happen. Maybe you heard about Erdős-Rényi graph. world of Erdős-Rényi. Erdős-Rényi graph, so you take the graph, the fully connected graph, but with probability P, you pick the link or not. So it's a random graph, right? With probability P, and each link are IID. That's Erdős-Rényi graph, right? So now you have a random graph, and you can have the same type of question. So, and actually it has been studied. Mean field game on the Erdős-Rényi graph has been studied by Delarue, and have some work done with a student also. And the mean field game, mean field limit is the same basically, because in the Erdős-Rényi graph you have a lot of connection, right? Not full, but a lot of them, and the law of large numbers have enough space to take place. Right? So Erdős-Rényi graph we know. What else we could do? Or any graph. I mean, say have a graph where the number of connection is random given a certain distribution. This is very complicated, and that's a lot of application in banking system, because you want, for instance, you want some agent which are connected to a lot, and some agent who are not connected to a lot, like central banks connected to a lot. So this is a very, very rich problem. Here we are just scratched a little bit on the two extremes. We do a little bit more. We did a little bit more by going to tree network. We look at tree. So a tree structure. You can understand that tree structures are much easier because you have kind of a Markovian setting. So we could generalize everything we did to tree network. Instead of one affected by one, you are affected by D of them, boom. Which each of them, so these D agents are affecting you, and then each of them is affected by D of them, and so it's a tree structure. So I'm passing the thing, you can do everything, you can compute everything. So the tree is a little bit complicated, but we can do it. So it's in the another extension. I mentioned the Erdős-Rényi, which is mean field game with some randomness. You could do directed chain with some randomness. Let's say, for instance, each link here is here with probability P. Yeah, that's exactly P. Each link exists with probability P. So now if you think about it, it means that one, for instance, will be in a finite chain. It will be in a finite chain, but with random number. Right? It's the length of the chain is random. That's finite. So that's interesting. So this is interesting, and you can do it. Same thing. You can go. You introduce in the objective function. You introduce your random variable here, and you can do the computation. There is not much big difference. They behave in the same way. It's a long computation, but they behave in the same way. So I want to stop there and see if you have questions.
So question or comment for a speaker?
Go, shoot. You.
Can I ask one problem? Actually, I have two problems. The first one is that you say a random directed chain. So does that mean if we only have not a periodic condition, that means you cut, then you have two different independent groups?
Oh no. So you mean if I compare the periodic boundary condition and the one with free boundary, let's say, when n goes to infinity, they are the same.
Okay, but I mean in a random directed chain case, because you say there's some probability p they don't affect, right? Yeah. For example, the first four players and the fifth player and second player, are they independent in this case?
That's why we consider that in the infinite case. Now you can start with an infinite number of agents, but only a finite number will affect.
Oh.
Because you cut the chain here. So all those will not affect number one.
Okay, I see. So it's become a finite player case.
Yes.
I see. Another problem is in the game you say when n goes to infinity, but I'm not maybe I don't quite understand. You say it's a summation j from 0 to infinity, right? So you have an infinite number of y, but how do you define the numbers here?
Yeah, but those numbers are given by they are given here, right? So these are the numbers have been computed. Something takes me forever. Those numbers have been computed, right? These are the numbers. You have them. They are here.
Okay.
So these are the weights. Wait, so you are attracted to all the others, a linear combination of the others, with those weights. And of course, this series conversion, they are nice relation on those numbers. They decay quite fast. I mean, you can analyze that.
Oh, okay.
So you are affected by the next one with 1/2. The first one is 1/2. You are affected with the next one with the next number, which is smaller. So the effect of number 3 is smaller. The effect of number 4 is smaller. It's a combination of all these effects, right?
Okay. So phi infinity will be 0 in this case.
Yeah, it goes to 0, of course.
Okay,
Of course.
okay,
Of course.
I see.
Of course.
I see.
Yeah, that's here.
Oh, yeah. That's my question.
So
Okay.
this series is converging.
Oh, converging.
Can you comment on this closed loop? What if in the closed loop system?
Closed loop and open loop. You should ask me.
Yeah, closed loop.
Closed loop and open loop. So closed loop, open loop is alpha is
Yes.
only a function of the Brownian
Right.
motion. Right?
Depend on
So
space.
the only thing is it has to be adapted. So it doesn't depend. You cannot, when you make your choice of alpha, you don't observe the x. You just know the Brownian motion.
Right.
As opposed, when you do, so it's open loop because it doesn't look at the x.
Yeah.
Now, closed loop, you look at the x, you have access to the x, and your alpha may be a function of x.
Yes.
Right? That's closed loop.
Yeah.
And so the difference is that in the computation, when you will put the alpha in your system, you will have to differentiate your alpha with respect to x. When you do dh over dx, you have
Yes.
to differentiate it.
Which
In open loop, you don't differentiate the alpha.
Ah.
Closed loop, you differentiate it. You
Yeah.
take your ansatz and you differentiate it. So the two systems are a little bit different.
Yeah.
And closed loop Markovian means it's only a function of xt,
Right.
not the full path. Right?
Yeah.
So for n players, the solution of the games are different. Not much, but they are a little bit different. But in this case, when n goes to infinity, they are the same. At the end, they are the same. That's why I didn't insist too much.
Thank you.
I have one question. So you mentioned about column numbers in your talk. You also mentioned about LD's running graph in your talk.
Yes.
As I know, column numbers are moments of weakness in a circular law. And if you look at the random matrices associated with LD's running graph, its eigenvalue distribution also converges to weakness in a law. So do you think there's any relation between the law and the equation that you consider?
I don't know. No, it's a good question. I don't know. Honestly, I'm not an expert in number theory, Catalan numbers. Erdős-Rényi is a very particular graph. The only thing I know about Erdős-Rényi is that when you apply the empirical distribution of your neighbors, it's a random number of neighbors, but there are many. So the law of large number will still take effect. That's all I know. Now you could do Erdős-Rényi with a p, which also scales with the n.
Yes.
So this will be sparse network. If p gets smaller as n goes to infinity, each individual will be affected by a smaller number of people.
Yes.
This is called sparse network.
Yes.
And that I didn't get into that. This is more complicated because then mean field gain doesn't apply, and so yeah, there is a lot of things to do. I think Dan Lacker at Columbia University has done quite a lot in that direction with Kavita Ramanan. You know Kavita Ramanan at Brown University? So she is doing large deviation and all this stuff. So they have done a lot of work in that direction, but I'm not discussing that here. Yes?
Okay, so I think it's time. So let's thank our speaker again. Alright, so the next one will begin shortly with a speaker.
It's now.